Now we're going to look at the present value of an annuity. We'll keep the same basic setup as the future value. So we have a recurring payment of big R, an interest rate of little r, and coinciding payment and compounding periods. Now first recall that with the simple compounding interest, P was the present value and S was the future value. This made sense because there was a single payment on day 0 and no other payments. However, this doesn't work with our annuity formula. S is still the future value, but R is now the value of the repeated payments. It's not the present value, so we're going to have to find it completely from scratch. We'll start by drawing out our timeline and sketching out our compounding periods, filling in our payments and their rates as reminders. Now each of these payments needs to be brought back to the present. This is exactly like when we were computing the present value of a bond. Each payment picks up a 1 plus r to the power of -1 for each compounding period through which it passes. So the total present value is the sum of all of these payments. All right, so when we're doing this in general, over say n compounding periods, we can tidy this up by using sigma notation. The r term is multiplicative and doesn't affect the sum, so we can pull it out. And this is again a geometric series, though this time there are different indices from the future value case. But we still have a formula for the expression. Now by writing out the sum in it a little bit differently, we can see that the common ratio in this case is 1 plus r to the power of -1. Thus, using our geometric series formula and putting 1 plus r to the -1 in place of the c terms, we get the following. And we can work with the denominator to get something which will simplify this expression quite nicely. So if we write it out and do some quick algebra, we can collapse this sum into a product. And see if you can look ahead as to what's going to happen. There's a 1 plus r to the -1 in both the numerator and the denominator, and these are going to cancel one another out. So the expression that we're left with is much more simple. If we also factor out a negative sign from the numerator, then we can write this as so. So to summarize, the present value of an ordinary annuity with regular payments capital R compounding at a rate little r and coinciding payment and compounding interest periods is the following. All right, so as an example, let's suppose that you work for a bank and you're approached by a retiring senior, and she wishes to purchase an annuity. All right, so when you purchase an annuity, what happens is the bank is promising to guarantee you a regular payment to your account in exchange for a large upfront sum of money. Some annuities have fixed lengths, like say 10 years, while others are guaranteed until you die, and so in that sense are insurance-like things. We're going to focus on fixed length annuities here because otherwise we'd have to get more into probability theory, which we just don't have. Now the annuity should cover her monthly expenses of, let's say, $2,000 a month for the next 20 years. If the bank uses a 3% APR compounding monthly to make annuity computations, then how much should you charge her for the annuity? All right, so the price of the annuity is the present value of the annuity. It's what the annuity is worth today. So we'll throw everything into our formula using a term rate of 3% divided by 12, and over 12 times 20 equals 240 payments. If we do that, we get $360,621.83. And so many of the applications that we had for future value also apply for the present value, and same sort of thing. You can go back and recompute the present value of bonds now using this present value of an annuity formula and see if it agrees with what you found previously.